Okay, so welcome to today's lecture in Advanced AI. As I already mentioned on Monday, there we started with the idea of how learning also can work. We looked at the first phase, like how you can do self-supervised learning, mainly and building initial models. And today we want to now look at the second step, where like once we build the initial model, how can we transfer this knowledge to new tasks? So this is, I would say, the dominant way of how currently learning and AI systems are built. So while like maybe 5 to 10 years ago, the default was you collect a lot of data, you train your model and apply it, we now see that typically you won't start with a random initialized model anymore, but you're doing this idea of transfer learning, that you have an initial model, you train it to have a basic capabilities, and then you adapt it to your task. How we can do this initial training we looked at on Monday, and today we'll focus now on the second step. So on our overall structure, we're still in this learning and data, and the ideas we'll cover today, they're maybe mostly like visualized on more text-based approaches. But this idea of doing fine-tuning and transfer learning is used for, I would say, all modalities and can be applied to all of the modalities. So what we'll look into is we'll first like motivate this idea a bit and then see how transfer learning works. So look at the different ideas of transfer learning. When we want to transfer learning, there's mainly like three main design decisions or some we want to do. So the first question is what to do about the architecture. So what do we, when we go from one model to another model, what do we have to change in the architecture? If we now learn additional things, where should we like store this information? We'll look at the architecture and then especially introduce this idea of adapters, where the idea is we have a large neural network and can we then plug in there some additional components which can do additional computation, so learn additional things. Then we'll look at training. So if we're doing the second step of training, how can we do this second step of training? How can we, starting from an initial model, learn then the second part and also learn that this model can do this second part? Finally, we will look into when we're now going from models that can maybe not do one single task, but several tasks, we have an additional challenge, because before it's clear what the model should do. I mean, if it has one task, you give it out input data and it should produce your output data. If the model should now solve several tasks, you not only have to give your input, but you also have to describe the task or put in your task information. And so we'll look how we represent tasks, how we can do that. And and especially go into large language models, because there we have one very new idea that we no longer have to have like more this discrete representations. You'll not have to tell the model like by data learn what to do, but you can insert instructions, natural language description of what should be done. And the model is then able to map this into the right instruction of what to do. But let's start for motivation with traditional machine learning. So when we're doing traditional machine learning, the typical thing we're doing is we have dedicated tasks. For each dedicated task, we have dedicated training data, and then we're taking this training data in order to learn our model. So for each task, if you're in some company, you have somebody asks you build a model to do document classification. The first thing is what you have to do is like collect training data. So you collect the appropriate data, then you define your architecture, and you'll train the model and so on. And that model is then only there for doing documenting. So for example, in that case, what you would select is documents or like a sequence of words. Then you would have labels for each one, what you want to classify, maybe things like news, research papers, blog posts, and so on. And if you followed this lecture, I am hoping you would come up to some of this type of architecture. So you put in this into a neural network with an embedding layer, some sequence layer, RNN or CNN or transformer, then your aggregation layer, and then you would classify it and train it with cross entropy. If then you not only should do a document classification, but also you should do named entity recognition, meaning you should classify that KIT, for example, is an organization. If your a company wants to have that, then you would train a similar model. You see the architecture hopefully would be a bit different. You would identify, oh, this is a sequence labeling task, so we need to do like one class for each input word. But you would have a very similar kind of architecture. You would have, again, to collect training data. This time we have sentences, and we have labels for each word, whether this is not a named entity, whether it's a person or an organization, and so on. And then you would train a new model, meaning you start with from scratch, randomly initialized model, and you train the model and do this type of tasks. If you would do, for example, medical named entity recognition, so saying that this is an illness and so on, you would again do this, train a model that does this and learn. And importantly, each time you train a model, you have to learn everything. You have to understand what the word means, what the word the means. If it's a vision model, you have to understand what are borders and so on. So every time you learn something new. Meaning what we're having is typically the task is defined by a data set and somehow what we want to learn, a loss function, and that is then what you do. Of course, what exactly a task is now depending on your task. Is medical named entity recognition a new task or just a version or like a different data set of general named entity? It's a bit of a question, but in general, we can, if we are just defining it by our data set and our loss function, we can always define one task and then train a model that does it. So we will always like build individual models for all the tasks that we're interested in. And the big challenge is that also means you always have to learn everything from you, which is, of course, a bit unnatural. So if you think about your own learning experience, I hope if you come into advanced AI, you're not starting from scratch again. You have learned a bit in your bachelor before, and you have learned something in introduction to AI, and all this knowledge you can use again and apply it here. And the question is, of course, should we do that the same thing in machine learning? So in generally, if you think about language, there's one example, but the same thing about images is that many of these tasks share general common knowledge. So you need to know a bit about the syntax, about the semantics. If you learn something about named entity recognition, that might be helpful in document classification. If you want to do named entity recognition about a medical domain, other medical text might also be helpful to do that. And therefore, the idea was maybe it's not the right version of always train everything from scratch, but to share knowledge between different tasks. And this is especially interesting or came very prominent in neural networks, because there we have one very interesting property in there, that we have the different layers where we do hidden activations there, and these do some abstraction of your input data. And what we'll see is that, these abstractions are helpful. They identify some properties of your data. And if you learn them on one task, they might be helpful on other tasks too. So there it's very easy now to transfer to other tasks because we have these representations of the input data and can use it somewhere else. If you think of more classical machine learning, like a support vector machine or something like that, you have a lot of features, and there it might be more difficult. There is no abstraction and different layers of abstractions to do that. With this motivation, people look now into different ways of how we can make use of training data in the one, apply it to the other. Again, even if we're only talking about supervised data, it's very expensive to collect labels for named entity recognition, for document classification, for image classification, for different types of image classification. So it might be nice if we can just use all the data. And that is like somehow the first idea. That's what is called multitask learning, where the idea is we're not training, you not see individual models down there anymore, but you're training one model which does all the tasks together. Again, then the idea is, of course, that the model should learn from each other. And especially if you have scenarios where there's limited data, this is a very successful data. It's a different view on like how it's done in traditional models. So in traditional models, if you would, for example, do named entity recognition, you would first learn part of speech tagging, like that is a noun, because that something is a noun is a very good indication for named entity recognition. So you would first do part of speech tagging, do this as a feature and use that for the other task. Here we can automate that a bit. We're just doing all the tasks which are helpful and jointly training. And if we learn something for the one task, we learn a better abstraction of your data, which can be then applied to the others. And this is an example. For example, also names might be typically important for document classification. So if you jointly train named entity recognition and document classification, you will have a better performance on that and be able to do that. This is the one idea where the important thing is here in the end, you're really interested in having good quality on all of these different tasks. What we are a bit more focusing today, but which is very related, is what is called transfer learning, where we have some source tasks where we learn general knowledge, and then in the end, we're mostly interested in one single task. I mean, often you're not interested in all the performance, but you're mainly interested in solving one specific task, and that's your target task. So what you then want to do is transfer this knowledge and be as good as possible on your target task. But again, when you're learning the target task, you don't want to start from zero, but the idea is that we start from decent, good knowledge and can transfer all this knowledge. So in transfer learning, we want to transfer the knowledge from the source task to the target task in order A, to use less data, or B, have better performance. And of course, this is a bit close correlated. One important difference to multitask learning is that typically we're not interested really in the performance of the source tasks, and we might take any type of source task. And that is then the connection to Monday. We might even invent source tasks, which are completely somehow useless. They're not really important. I mean, filling out an image, said maybe useless is the wrong term, but mostly you're not super interested in that. But you're inventing tasks here. You can even invent source tasks in order to apply them then and just learn general knowledge on. So the general idea of transfer learning is this idea. We start with large data, we train then our pre-trained model, so that is the source tasks here, that we do the first step of training, where we start from large data and pre-train. And then we have this initial model where hopefully a lot of knowledge about how to deal with a modality, with the data that we're interested in, is encoded. And then you're starting from this model, doing your task data, and do the learning. And the important thing is, of course, that this learning should be more efficient. You don't have to learn everything from scratch, but you have already a good representations. You have learned a lot of good information, and then the learning from the pre-trained model is more efficient, meaning you can have larger models with better performance, or you need a lot less data to do your final task. So again, from our example from the beginning, if we're having the model knows already what named entities are, it might be easier to transfer that and build a good model which does then document classification. So again, we might be significantly more efficient in doing our final learning compared to an approach where we don't have these abilities. And very important. So the difference is we're having on the one hand multitask, where we are trying to have the ability to perform like all these different tasks. And then the other idea is that we have transfer learning, where we are only important in the performance on a single task. That also means, which is nowadays often happened, we might have not access to the training data or the data to train your source model. So how, if you're now build large models, often you might download pre-trained models trained on mainly the internet, and you might not be able to download the data because it's just too much to have and license issues. So you don't need access to the model. If you're only interested in doing the transfer learning, it's enough to just get the model and continue from there. We'll see it, of course, depends a bit. There's different learning to do the transfer learning, but this is by now even the default case to do that. Also, if you only do one single task, you of course don't have to think about this problem of task representation because it's clear what the model should do. And then finally, of course, you can also combine those things, and that's today also very common, meaning you can do transfer learning and multitask learning, meaning that then in the second step, you're not optimizing for a single task, but you're optimized to do several tasks. So if you think about current state-of-the-art language models, they are typically not good at like one single specific task, but they are first trained to do next word prediction. Then they are normally trained to follow your instructions. And now, of course, the question is instruction following one task? Or since instructions are quite broad, you can also call it a lot of different tasks because they can do machine translation, they can do document classification, and a lot of other things. But in general, I mean, what you're like, again, it's also, of course, a definition of task, but it doesn't need to be one very single specific task. We can also do more learning here and have several tasks. At the very end, we'll even come to like looking into zero-shot tasks, meaning can we also somehow skip the last layer, the second part of transfer learning, and learn an ability that we can also solve tasks without dedicated training data. And so can you also then somehow transfer your knowledge to new tasks without doing final training on them and being good at that? But yeah, how exactly that can work, we'll have it at the end of today's lecture. Why should you think this is important and why should you have this knowledge? Here, a bit of an example. So this is the performance on named entity recognition. So we have this problem of named entity recognition, you know, like whether this is a city or something like that. You see that by now the performance is quite nice. We already like for 20 years now, we are around like over 90%. But maybe the interesting thing is from 2009 here to 2017, not that much has happened. So this is one evaluation. And you see, yeah, they improved by 0.1, 0.2%. So things were relatively stable, not a lot of things happened. And then we're seeing from 2017 on, people started to use like transfer learning, use a lot of models, which can no longer only learn from dedicated named entity recognition data, but they can encode a lot of knowledge by pre-training things. And you see that suddenly performance goes up quite a bit. Definitely in these 2 years, like significantly more than in the 10 years happening before. So you see this idea of using pre-trained models, encoding the knowledge gives you a lot of new opportunities because in a lot of specific tasks, you're in this scenario. You have only like small in-domain data and you want to learn, to be really good, you have to learn a lot of complex things which humans can learn while growing up and experience the world. But if you only have like several thousand sentences to learn from, getting what is an entity and what is maybe thing is for most things it's possible, you get over 90%, but then the real difficult problem starts and where things are really important. You also see that things then got much bigger. So this is like the size of the model, we had that. So you see that from 2018 on, really the size of these models exploded, which also is due to like that you can use self-supervised learning. You have a very large data set which you can train on, and then you can encode a lot of knowledge there to do then the next steps. Good. So let's have a look a bit more on the details before we start to go into the into building the models. But before we are doing the details, do you have any more questions? Anything actually? Good. So this is a bit for today. The overview on the on transfer learning, which hopefully should show you the two important steps. So the first one is like the pre-training step, where we train on the source tasks, and then the right thing is the fine-tuning or like the adaptation to the task. Just a brief recap on the first tasks, and then we'll mainly focus, of course, today on the so the pre-training is here, or the knowledge, what you want to have is encode as much knowledge as possible into your pre-trained model. Therefore, it's important that you have large amounts of data. And hopefully you remember from Monday, if we want to do that, if we want to really have large amounts of data, the successful approach to do this is to use some type of self-supervised training. So typically next word prediction, or like if it's more encoder style, masked language models. So some of these are here because then we don't need dedicated human labeled data. So human labeled data is always expensive. And that is the great idea of self-supervised learning, that we can do this first step, the self-supervised step. Maybe that again highlights a bit compared to Monday why this is interesting. So how that is then typically done is, as we saw last time, for example, with a language model doing next word prediction, or like at the beginning of this, at least in language for this one, it was encoder-based models, which just do like encode the information, and masked language model. And nowadays we see a lot of these language models which do next word prediction. Okay, so then the next step we'll want to look today is, okay, how can we do then the transfer? So now what we have is the difference to supervised learning is that we're not starting with a random model, but we're starting with a pre-trained model. We have our task data, and then we're doing the learning. So it's very similar to the supervised learning case. In this case, typically our task data is supervised learning task. If we want to learn some specific task, I mean, you want to have data that's at least a common thing. So that is good. So it's very related to what we have done and seen before, but we have to address some additional challenges to do. So it's typically that we have limited data, then transfer learning works good. If you have huge amounts of training data, it's not that important to train. I mean, nowadays there is no task nearly with huge amounts of data, because in pre-training, just the scale is several dimensions higher, but still you have more benefits if you have data, which is, so what is then different is, okay, if we start now from the pre-trained model, we can somehow keep this information. So the question is, which information do you want to keep, and where do you want to add the new knowledge, the task-specific knowledge? And that will do first thinking about, okay, how can we like do this trade-off between, on the one hand, you want to keep the knowledge that you have, and on the other hand, you want to add new knowledge. So how you can efficiently add new knowledge without deleting the other knowledge is the first thing that we're doing, and sharing where it's more about the architecture. How can you like put this into the architecture? Again, by your architecture, you typically define some biases, and this is the main question. Then the next thing is, if we have defined our model, we have to do our training. And how can we do our training? Now, starting not from nothing, but starting from a pre-trained model. Luckily, this is very straightforward, at least a very strong baseline. The nice thing is you have learned how backpropagation and gradient descent with normal supervised training works. And in fine-tuning, we can do mainly the same thing. There's some more decisions we have to think, but that is mainly it. And finally, we have to maybe, if we're having several tasks, we have to think about how to represent your task and do that also. So when you can do that, then you can, for example, think of these scenarios that you have a lot of large training data, that's your pre-trained model. You can now either do individual fine-tuning on general named entity data and medical named entity recognition data, or you can jointly do that. That's again the question. Do you do one task, several tasks? But that is a bit the scenario. So we have our pre-trained model, we train on that data, and then depending on our final, we use small amounts of this data to train them. The challenges we will now address is first the architecture. So mainly putting a bias on which information to take from the pre-trained model and where to put your new knowledge. Again, thinking about that you don't want to remove the important knowledge that we have. And then the same question is there when training. So how do you prioritize how to keep prior knowledge and not, but also learn the new knowledge? So that's very challenging if you now fine-tune. There is a term in neural networks called catastrophic forgetting. So if you do the learning wrong, it means you forgot what you have learned in your pre-trained model. And then, of course, this is no longer successful, because if you have forgot everything which you do in pre-training, this very expensive learning is somehow no longer there. Good. With this, we'll go to these three different tasks. But before we're doing that, do you have any questions? Yes?
So they, when it implementation say according to when they say data bring or information to the body or the sort of add or the transfer learning, is it like we add like a regular equation to those functions?
I mean, we'll see that. That's like the advanced step that you can do, like regularization. You can say, oh, learn something, but keep it as similar as there. We'll have that as advanced technique at the end. The first thing we'll see now in the architecture, the easiest thing is like what to freeze and not to freeze. So what part of the model you keep and which models you allow to change. And so, I mean, that would be the most straightforward way, but what you exactly say is like more advanced technique, which is also there. So the first thing is that you can, in the architecture, is like what type of the model do you keep? You remember we had Monday different types of pre-training models you can do. So for example, you could say the minimal pre-training in a text base would be that you only like take the pre-trained embeddings here, train them, for example, with Word2Vec or something like that. And all the other things of here, your named entity recognition system, you train. So your RNN layers and so on, this is all trained from scratch. And the only thing you take is the word embedded. So typically, that's maybe a good point, is you start at the lower levels. That's more what you what you keep, and the higher levels you might learn. Again, the idea is also in the neural network, we learn more and more. We first have more general knowledge, and then we have more and more specific knowledge. And therefore, it might be good to at least keep the word embeddings, and then maybe not keep the other things. Is this really little sharing? Yes?
Yes, it depends on the model architecture. It's like not a big model, then already the embedding model can be like the major part of the parameter. So it could be not the little part, but like the bigger part.
Yeah, exactly. So you have to be careful on like just by number of layers doesn't say you too much about how much you share. So I think this is the typical calculation of like how many parameters you have in each layer, and especially the embedding layer, since you start with your vocabulary in there. So you put in the full vocabulary, maybe 50,000 words, and map it to then your small hidden size. It has like by far like more than 90% of your parameters. So, and that maybe explains to you how where even like small pre-trading helps you significantly, because by just like starting from this one, you reduce your parameters by like from 12 million to 0.5 million. So you're already sharing a lot of knowledge and you have to learn a lot less. And this makes even this little sharing already very, very efficient, and enables us to maybe then only learn the things which are really specific on the top layers, but keeps the others. Of course, you can also go into the other extreme, and that means, okay, we share nearly everything. So if you have, again, a sequence-based model, you share all this. Does anybody remember how we phrase these types of representation here? Had that on Monday. These were before were static word embeddings. We had the output of the sequence layers on the top. I recall contextual word embeddings, because the important difference is this representation here, for example, should also represent the word diagnosis, but it represents it in the current context. So it does not only depend on diagnosis, but depending on in an LLM, it also depends on all the previous words, and more in the BERT-like model, it depends also on the future. But so this representation is no longer a static word embedding where you have the same representation for the word independent of the context that occurs, but you have a representation which depends on your current context. So you can use these contextual word embeddings in a language model, or especially we saw also the picture on BERT-style models. That's a typical way. And what you do is now you train the model first, for example, with your language model loss. So you always predict the next model. And now what you only have to change is on top of that, here the heads, which are now like no longer predicting words, but predicting your classes. That, of course, we have to learn. I mean, if you want to now classify things and the classes haven't been seen in pre-training, you're going to have to tell once the model what are the classes. But the idea is that this information of which class there is already relatively obvious in your hidden representation. And then this problem is hopefully not too complicated, and you can only learn this one layer. So this sublayer is what is typically called then in machine learning this classification hat. So what we have there is input is our hidden state at each position, so contextual word embedding. So if you have something like a BERT model, it means on each position here, you have a hidden state with a fixed size dimension. And what you now can put is you put the same hat on each of the positions. So that means you're learning a mapping from this hidden state to the class you want to do, and this mapping is always the same. So you have to encode all information on your input in your hidden state. And the output is then the labels, meaning you have to do here a layer which is a softmax layer typically with number of classes. So if you want to do named entity recognition, it's maybe like something like 10 classes. And then you do a softmax of that so that you get a probability distribution. So if you think about the parameters, this, if this is 250, here is 10, so you have something like 2,500 parameters, and that's all that you need to learn. So you see then in this case, learning might be quite efficient because you have very few parameters that you can adapt. Of course, it only works if this representation here is really very helpful and it's easy to extract that from there. Now we've seen a bit like the two extreme cases. The one we do very small input, and once we mainly keep the model itself unchanged and use it. Of course, there's also ways of doing it differently, and the one which is currently used most is what is called adaptive. And the idea is, yes, we want to keep all the knowledge in between, but we don't want to change the whole model here. We want to fix this and only learn a bit of what we need to do differently. So we know how things are nearly working well and how to encode things, but maybe for this task, some other information are important. So what we'll do is in each layer here, we add some extra computation, which allows us to do task-specific things in there, in addition to what we anyway do. These are nowadays called adapters and are like the default thing if you want to like optimize some pre-trained model. Especially that we'll not cover here, but one big advantage is that you can keep this model fixed. All your computational resources are then significantly lower, so you can do this type of training very, very efficient. So let's look into a bit more details of how these adapters work. So the idea is you have a layer, the layer gives you some hidden representation. At each position, for example, you have the same operation there, different hidden representation, and then the output of layer I is used as input to layer I+1. Now there's different ways on how to put the adapters in there. We'll here only look at the basic ideas to put them between the layers. There's also other works of putting them parallel to the layer. But the idea is now, if this hidden representation encodes information about the word, can we adapt this information a bit to maybe change them in some way that is like what is important to learn for the current tasks? And the idea here is you put in this called adapter so that the output of layer I is no longer directly used as input of layer I+1, but what you're doing is you first do some additional calculation on that and use that then as output. How we can do additional calculation is very easy in neural networks. The easiest thing is we just put some forward neural network layer in there, meaning so the input is our hidden layer. Now we are trying to generate a new hidden layer. The calculation of the new hidden layer is just we take this input, multiply it with a weight matrix, do some nonlinear function on that, and that is the output. Of course, that shouldn't change too much. If it changes too much, layer I+1 gets input, which is completely unusual, so it might not work anymore. But if you do minor changes, that typically works. And we can train then this adapters to learn things which are very important for our task. Which now it looks very nice. We have this small adapter in there, which changes a bit, and we can just learn these things there. Do you see any challenge when we're doing this? To think about how many parameters we add again. Yes?
The adapter has the same size as all the other layers. So basically you're just adding the additional full-size layer.
Yes, so it's not, I mean, I put it, it's a small layer, but it's not really that small. So what we do is, if you think about your hidden representation has maybe 1,000 dimensions here, then you're putting 1 million, like 1,000 times 1,000 parameters in here. So in each layer, you'll add 1 million parameters. So in total, that might be as much as you have anywhere there, or at least not significantly less. And I mean, that was the main motivation. We wanted to add these adapters, then we only change a bit, that we have only very few parameters, and then we can apply them. So by just like adding directly these adapters, that might not be the best way. If you just add a layer into your network, which this mainly is, it's significant amount of parameters. If you do that between each layer, you mainly double your parameters, and that's not what we want to do. So we have to do something else. Luckily, neural networks are very flexible. And the interesting thing is we can now even increase the layers but decrease our parameters. How does it work? We're doing what is called the up and down projection. So what we're doing is we're taking our input, we are down projecting it. So we have a first layer, which is a down projection into a new hidden state H hat, and then we have the up projection again. Why do we need to do the up projection again? Of course, the input and output dimension has to be the same, because the layer I+1 is assuming this dimension as input, and we don't want to change the previous layer. And so if we're doing that, how many parameters do we have? So you see here we have two simple layers. The one is multiplying H with WD, so the down projection, then doing a nonlinearity, and then we're doing the same thing with the up projection. So how does it work? How many parameters do we have? So if we're going from our hidden size n to our downsample size d, and then up to n again, then this here has a size n times d, and this d times n. So in total, we have 2 times n times d, a number of parameters. We're calculating that now, and assuming we're going down to a size of 100 from like a hidden size of 1000, we are going down to a size of 100 and then up again to 1000. Then we have now 1/5 of the number of parameters. So we have only 0.2 million instead of the 1 million parameters of the form. So even with add additional layer, we have a lot less parameters because our hidden size is smaller. So this might be a very effective way of doing a significant reduction of the number of parameters that we are having. So that is very good. Do you see any problem which might still be there? Yes?
We already have a very good embedding. Now we like discard information because we bring them. And so we assume that the embedding is not optimal, so we can't do it.
Everything is right. I mean, assuming that the embedding is not optimal, I would even assume so. So typically the parameters are over-parameterized. So there might be some way where you can shrink it to some degree, but most probably you'll not be able to shrink it to 10 by a factor of 10. And most probably the embedding you learn there is also not optimal. So your point is completely right that we are removing a lot of information there, and that might be like lower quality because everything has to fit to this bottleneck. So we have to do something else there. Luckily, there is a very general idea of neural network that works here. And the idea is, okay, maybe the adapters should not learn how to map or how to like convert that. But what we only want to learn is what should be changed on the hidden representation. So instead of learning a complete mapping of the hidden representation, with this small network, we only want to learn a bit, okay, what do we need to change on this representation? So that we don't have to convey all the information through the bottleneck, but we can maybe bypass that. And through the bottleneck, we only put what needs to be changed. And that's very easy. It's called residual connections. What it means is that our output is not the output of this network, but we take our initials, so our input, and add these things to it. So now we no longer have to learn how to map our input embeddings to the new ones. What we instead learn is what do we need to change on that. And that is a lot easier. And we don't have the problem we had before, because now the restriction we have is everything that we learn new, that should fit to the small embedding, but we don't need it for all. So by having this residual connection, we are preventing this problem. We can directly go and we can now just learn what we need in addition. So this is a typical setup of adapters where we can do things this way. A variant of that is also where we can do it in parallel, which can be either parallel adapters or you can view it as a weight factorization. So the idea is similar, but now we're doing just this type of calculation in parallel. So instead of what we had before, typically in your neural network is some type of matrix multiplication. So you multiply your input X with your shared matrix and get Y. What you can now do is, instead of only taking this shared matrix which you have pre-trained, you add two matrices to that together, like some multiplicative and maybe some bias and additive, and you learn this. Again, you have the problem, if you these matrices to be like point-wise multiplication and point-wise addition, they have to have the same size. So if we really take the full size of them, that wouldn't be helpful. What we can do is then a parameter efficient representation of the matrix. So for example, if you're taking just a vector, two vectors, and multiplying them in the unusual case, so not like row and column, but column and row, then you'll get, like from two vectors, you get the full matrix. And so you can have here a lot less parameters, because then you have just two n parameters and not n square parameters. So to generate this n times n matrix, you only, I mean, of course, you're not completely free then, you're restricting yourself, but using this representation as a product of two vectors, you again do this type of representation. If you do it in this type of representation, it mainly means you're going to one single representation here in between. So then you have also two vectors. So if you have here like one-dimensional, you like have one vector which you multiply with this one, you get here, and then you're multiplying it again, and then you get this thing. So in general, you can do the same thing here and get then a parameter efficient representation of that. Good. Any questions about that? Yes.
Specific weight piece.
Yeah.
Definitely have to sort of have a less smarts so that they can their representation would be
I mean, this is now, that's like typically then a hardware parameter, which you, I mean, easily can be seen here. So, I mean, the sparseness is a bit like the representation here of the hidden size. So the smallest one would be something like 1, then you have just two vectors to the maximum. And that is now a parameter depending, for example, on how much task-specific data they have, because you're controlling how many parameters you have. If you have more parameters, it means you need more training examples. So, I mean, it's not directly sparsity, but it's mainly like how much parameters you have, how much power you have to change your model should depend on how much training data you have. And also, like, you might use it on some part of the network and not others. So there's a lot of work on that, for example, on self-attention. Should you learn all the parameters? Should you only try to learn the queries, only the keys, and so on, or only the linear layers in transform? Yes.
If I represent the matrix as this other product of these two vectors,
yes.
What will then happen during back propagation? Because like we will not be able to maintain this form anymore.
No, I mean that's just math. So it should you can do exactly. I mean this is completely math. So you can just doing back propagation. You can do exactly the same calculation. Everything is derivable. So differentiable. Sorry. We can do. I mean do that exactly during doing calculation. What you then, of course, in backpropagation do is that your shared metrics, for example, you're not updating. So you're ignoring all the updates and you're only updating then the weights which you're allowed to share, to change. Good. Any more questions? Thanks for them. Any more for the architecture? Good. Then let's have a look how the training works. And the nice thing, so we're again at this general framework. We have now defined our task-specific model. Now we have to train the model. And the nice thing here is it works, at least the baseline works very, very similar than the others. So what we can do and what is nice in neural networks is we are not forced to start from a random initialized model. So if you remember how backpropagation works, you randomly initialize your model and then you do gradient descent to do that. Now in continuous fine-tuning, the successful idea is, oh, we just continue doing that, and that works very well. So when we're doing a normal neural network training, we have our training data on the left. And then, like for each training example, we calculate the forward path, we measure the error, make then the backward pass, and do our weight updates. And this way, we're going through all the training examples that we're having. So we're doing that for the first, the last, and typically then when we're done, we're starting over again at the beginning and continuing doing that. So we're over and over and over, always going through all your data. And what we have now, this is some of the pre-training. We are done with this. We have now our model. And this iterative training is now the nice thing. What we can do is we're just continuing with the task-specific data. So we're even allowed to change our models. What we have to do, we add adapters, we add our classification header. So then we're taking now our small transfer learning data, and we can just continue and change our parameters furthermore. We don't have to do any type of different learning, but what we're just doing is now we're iterating now through this data and doing exactly the same process. We're calculating the forward path, we're measuring the error, we're doing the backward pass, and then we're updating our weights. So that is first very easy and nice application, meaning that we don't have to invent any type of new type of training algorithm, but we can use the same type of training algorithm. The gradient descent doesn't find an optimal thing, which is normally not good, but through this iterative process that we are slowly updating, it doesn't force us that we continue with the same thing. We can also switch the model, we can switch the data, and just continue with this thing. But of course, there is some things we have to consider. So first of all, like what to do with the new parameters. So now you have new parameters. The new hat, we have the adapters if you add them and so on. So you have to do there something, and there it's quite clear what you do is you do random initialization, and then you continue training with your task-specific data. You have to be sometimes a bit careful. So for example, if you add adapters into it, you maybe should initialize them in a way that they're not doing too much harm. Because if they are like randomly disturbing all your others, then you're not learning anything helpful anymore. But especially if the new parameters are on top, that's working quite fine. I also like as a motivation to maybe more change or add something on top and then not add something at the bottom, because if you add something on the bottom, this is input to what it was learned before, and it's a bit harder to map that to what was it. And if you have that, so these new parameters is quite. The other question is what you do with your shared parameters. So we said we are using some of the information, all of the information we've seen that in the architecture, now also doing the fine tuning. And there's like mainly two ways how that can be done. The one way is to freeze them. So you don't change them, you keep them, and you only change the new parameters. This is fixed and will not be changed during gradient descent. It also works fine if you learn if you see the backpropagation at what it means. Yeah, you're backpropagating all through your model, but then you're not backpropagating toward the weights that you don't want to change, and then you don't do weight updates for them. So that is also quite straightforward. in neural network learning, we don't need to train always everything. If we only train some part, these weights will normally adapt to be best performance given the other restriction. I mean, it's even our initial definition, because we're always optimizing each weight in a way that we're assuming nothing else changed. We're not doing that, but therefore it doesn't really matter if now the other things don't. The other option is, okay, we can also update them, so that also works fine. So you can, instead of keeping them fixed, you're updating them. So you're just not starting from random initialization then, but we're starting from a good starting point and now only adapt them first. The trade-off you have to think about that, and there is, for me, if there's two options, it also means there is no clear winner. So there is not that always the one is working better or always the other is working better. But yeah, sometimes the one is better and sometimes the other one is better. And that, for example, depends on how much training data do you have, because there's a trade-off. On the one end, you want to train as few parameters as possible, because then you're preventing overfitting because you have not enough data. On the other hand, these parameters are not optimized and optimal for your task, but they're optimal for your pre-training task. So if you're not optimizing them, you might not come to the somehow best performance that you can achieve. Any questions first to general idea? Yes?
Two apart options, or is that something like a continuous increase, a gradual increase towards which is more flexible towards later layers maybe?
Yes, there is thousands variants of that. I mean, this is the two, again, maybe most extreme case, and there's a different ways of what you can do. You can have what we mentioned before we come to that, you can have a loss that tries to keep the model as similar as possible. You can identify weights, so that's called elastic weight decay. We're not doing that here, but the idea is, you're looking in your big network, what shouldn't be changed, which is not important initially, and then you add the new information into there. So there's huge amount of work on how to best do this fine-tuning. So you can do there a lot. The nice thing is maybe that this basic works decently. So you have a good starting point, and then depending on your task before, other things might be better. So to summarize again a bit these two extreme cases, there is the somehow extreme case of what people may refer to as feature extraction, where you, for example, freeze all your shared weights, and there can be then a lot, and then you only update the new hats. So that would be the one extreme case, and you really keep everything, and if you have very small data, that is the right way to go. The other extreme is full fine-tuning, where we initialize with a pre-trained model, but then train everything. So we are really changing everything. That means you again need a lot of training data. And between that, of course, there's a lot of differences. You might not decide the same thing also for all layers. It might be, you're taking the top layers as initialization, but allowing to change them, and the lower layers you keep fixed. Because there is one additional constraint. On the one hand, it's of course, you need enough data to do good training. On the other hand, there's also memory issues. If you update more parameters, you have to store all the gradients. So especially if we're going to very large language models, people also might not do the full fine-tuning because it's just not possible on consumer-grade GPUs. And then you can do these adapters. So if you use adapters, the common thing is that you're not changing your model. I mean, of course, you theoretically could add adapters and also train your weights, but this is a bit why to add adapters if we're already changing things. So typically, if you add adapters, you train the adapters, and of course your classification head on top, but the other parts of the layers are kept frozen and are not changed. Because if you change them, then somehow the use of adapters is not useful anymore because you can change them. And it has, I mean, there is also like a big memory advantage because for all the weights that you're here using, you don't need to store the gradients and you only have to store the gradients for the small adapters. Of course, during backpropagation, you still have to backpropagate all the way down. So that's of course the big advantage. If you only train like a feature extractor, you have to do a forward pass, but the backward pass, you can already stop here at the first layer because we are not changing anything there. So the training is a lot faster that you don't have the full backward pass, but only do the backward pass there. Yes, so as I said, so the common idea is that you do binary decision. So either you update or not. So that's or the common or the baseline. But now there is different ideas of what to do additionally. For example, you can do try to update all parameters but minimize the changes. You can try to avoid overwriting useful information, or you can try to maximize some of the positive transfer. And we at least want to look at two examples how this can be done. So this is idea when you're not happy with your baseline decision, what can you do better to improve this type of learning? One idea is what is called discriminative fine-tuning. And there again, the idea is in the lower layers, you have the more general knowledge. And then if you go up, you're doing more and more task-specific things. And that means, okay, if you now fine-tune to a task, you mainly want to change the top layers and you not want to change so much the lower layers. You could do that, of course, as a binary decision, saying half the layers I put in, for half the layers you put, you freeze them and the top half you change. But you can have it also more gradually. And the easy way to control that is the learning rate. So if you remember, we calculate the gradient, and then we're multiplying this delta with our learning rate to add this to our initial weights. So the learning rate like controls how much changes you allow for the different layers. So if you have a large learning rate, if you do it in the gradient descent, it means you do big jumps, while if you have a small learning rate, you only do like minor jumps. And now the idea is maybe it's good to have different learning rates. So on the top, you have a large learning rate, meaning that you can jump quite fast. And if you have lower layers, you have a smaller learning rate and you're doing. So for example, you take your initial learning rate and then multiply it with d to the power of minus e. And so you have a lower factor here down there and then a higher factor up there. The other thing is what we had already before is to add regularization. So now, I mean, there's general works on regularization where you say you try to like prevent that the model changes too much by restricting the changes and only allowing, for example, that the model can most of the values should be around 0. Now I mean, that's a more general restriction. Now we have a better estimate. We know our initial model is quite good. So what we then can do is we are now restricting ourselves to, it should only change from this initial model, it should only change something if this is really helpful. And the more you change, the more you penalize it, and you prefer models which are more similar to your initial model. You can do that just by having a similarity loss. So you take all your weights from your initial model and from your current model, you do the difference, and then you're keeping the model as similar to your initial model as possible, and allowing only for really changes if this is in some way helpful to do. Good. Any more questions to the training? Okay, then for the last 20 or 25 minutes, what we now want to go is to a bit more the multitask steps. So now we had always a case we are doing transfer and we want to solve one task. And now you might be interested in not only solving one task, but several. But this gives you additional challenge, because what we now want to tell the model is not only given this input, do this output, but for the same input, it might generate different inputs. So your input does not only have to be your data, but it also has to be, okay, the task it should solve. So if you think about document classification and named entity recognition, you give it a sentence, then the model could generate a classifier, or it could generate the named entity recognition. You somehow have to tell the model, now do this. And another example where this was commonly used is if you do multilingual machine translation, so you're generating into many translations, you have one translation system which can not only generate into German, but also to French, Italian, and many other languages. Then, of course, you have to tell the model what you want. If you just tell the model translate, then it will randomly select one of these languages. So we need a way to tell the model, okay, what it should really do. And the nice or good thing is, this is very easy in neural networks. Already in the multimodal lecture, we saw we can just put anything into a neural network typically. You just do have to learn an embedding into that. And therefore, this is quite working for this also. So what we can do is we can learn now task embeddings. So in addition to our normal text input here, we have a task embedding, which is the mapping from the number of tasks we have. So maybe very few, 5 or so, again, into an embedding vector, and then we can just prepend to that. And now the model can learn, okay, based on this embedding, I should do the one task or the other task. So if it's named entity recognition, I have to label this. And if it's document classification, I have to label them as the other. So that works very nice. If we always know the task, we can give the task and then learn a task-specific embedding. And this task-specific embedding will tell the model what to do. Again, one of the really big advantages of neural networks that they can handle very different types of data. So you can view the task description, the task tag is also like just a modality which you put in there and do. So therefore, it is good. Now, you might want to do also somehow new tasks. So if we talk about the zero-shot task, so if you're just imagine, maybe you can do named entity recognition on news data, you can do document classification on medical domain. Now you want to combine you want to do named entity recognition on the medical domain. So how can you do somehow a new task? If you're doing this, you have here you give document classification on and it can generate that. But of course, these embeddings are only learned for the tasks that we have seen. So we can't do it for a task that we haven't seen, because then there is no embedding trained for it. Or you can, of course, you can always use a randomly initialized embedding, but this will not be useful. So any ideas how you can address this problem? Just imagine you have document classification on use in medical, you've named entity recognition on use in medical, but in training you only have now seen 3 of them, and named entity recognition on medical you have not seen in training, but you want to do that. Any idea? Yes?
What we discussed earlier, you reuse some of the one model that does already that learn the embedding for the standard domain, and somehow add the classification header from the entity recognition of the other model, and then do like a bit of adaptive training to merge the two or something like this.
But I mean, yes, that it would be the right go when we have some adaptive training, or a good possibility. the problem is we're assuming we might have no data. Maybe it's not realistic anymore. You always have some data, but can you think about it? So that's exactly there. So in this type of combining different ideas is very good if you have some data to adapt things. But if you don't have the data, and maybe you even want to be able to solve all 4 tasks, the easiest way is we can look into more modular representation. So what we, for example, can do is now we have somehow the domain and the task, for example, and maybe we have not seen all combinations. So we can now add like one saying this is computer science and this is document classification. And then if you do this modular representation with 2 tags, you don't have to have seen all of them, but in training, you have to, for example, see document classification and computer science and identity recognition, and medical and named entity recognition. And then in tests, you can do medical and document classification. And now it has seen all the things, just not in this combination. So it still might not be as good as if you've seen it in training, because it has to somehow learn also like unusual combinations of that and be able to classify them. But not like perfectly working, but by having this modular representation, at least each of the embeddings we had for both position should have been learned, and then you can like recombine them in a new way. Any questions to this? Yes?
With these like task programs, can you drop it from the dense embedding there as well?
Can you?
From the dense embedding, because if you have like dense embedding of words, for example, or dense embedding space, you can kind of guess within your own this relation to like capitals of countries or the countries themselves. So if you have a similar embedding for like task programs, and you also like just guess, so for example, a new field that's not medical and not computer science, but you know we have no relation to something that people kind of just guess embedding tokens from those space.
So now what you're assuming already is that this medical token is somehow similar to the word token for medical or so. In the basic setup, that might not work that well, but you're going into the right direction. What you really want to have is you want to have a natural language description of what it is. So this is the medical domain or something like that. So that you have like you can use your word tokens, maybe also describe your task, and then use that. And this is one of the very interesting things that we want to look last on, and that is what is done in large language models. Because instead of having artificial tokens that we had before, which are not connected and where we do this modularization ourselves, the idea is then that instead of using that, we can do a natural language description of the task. So a very short one would be translate. A longer one could be, can you please translate this sentence into English or so? And then you put your input. And the interesting thing is that works with large language models. So you have a different way of describing your task from the discrete representation we had before. One big advantage, and that will come as like also like more transfer even, is in large language models that we can now go for natural language description. So we're just describing the task, giving our input, and then we are generating the output. And that again is then successful, especially successful in this zero-shot transfer. So although we are training the language model, maybe even only on next word prediction, we can transfer it to solve a lot of tasks, which we do in natural language description. So how does it work? Why does it work? At least some motivation for that. So remember, like, how does a large language model look like? So the architecture is typically our decoder-only model. So we always do the next word prediction. And then typically we're using a transformer. The transformer is not unimportant. So in this type of learning, we need a lot of context. And this type of learning where we can use natural language descriptions is very helpful to do that. And we'll have typically not as shown here, like one sentence, but during training, we have we have several sentences so that we really learn like long contextual tasks also. In our pre-training, we'll then really have typically in the first step only our next word prediction. So we are doing our pre-training with only the next word prediction. That's a typically large language model task. Now, what they're really good at is now the so-called zero-shot ability. So they are able to now, in the transfer learning setting, I mean, our source task is only next word prediction. What we now want to do is solve some other tasks and do them also good. And the idea here is, so you can on the one hand view it as we do a natural language description of your task and solve the task. The interesting thing is, or the other way of viewing it is that nearly all tasks that are out there, you can transfer into a next word prediction task. And that is what you're often doing in large language models. So that therefore next word prediction task can also be anything because mainly all tasks you can do into a next word prediction task. So how does that work? So if you have the task named entity recognition, so you have a sentence, I fly to New York, and you want to make now named entity recognition. How can you do named entity recognition? You transfer this into a next word prediction task. By doing this, the sentence, I fly to New York, mentions the city. And then if you now have seen a lot of data, hopefully the most probable continuation of that is New York City. So what you have mainly done now is you have transferred, you can again view it in two ways. Either you can say, oh, you have a natural language description of the task named entity recognition, or you can say we have transferred named entity recognition in a next word prediction task. So that enables us to really like solve things in a zero-shot way. So you have now not trained the model to really do next word prediction. To named entity recognition. You have only trained it to next word prediction and then use it. The main name for that is prompting. I guess you all know that. What you're really doing there is you encourage a pre-trained model to make a particular prediction based on the. And the interesting thing is that you can solve a lot of very different tasks by this. I mean, maybe you've seen more negative view on prompting because, of course, it has challenges, and if the model is not good, you have to be very specific, and with some prompts it's work and with others not. But the interesting thing is that we can view a lot of these tasks as a next word prediction task. So, for example, if you want to do question answering, and you want to know who developed JDK, you can transfer this question, who developed JDK, into a next word prediction by starting JDK is developed by. You can do JDK is developed by, put into your language model, and then just check what is the most probable continuation. If the model has been trained on a lot of data and knows that, then hopefully it should be Oracle. If you want what are the abilities of birds, you can do birds can and it should answer fly. Maybe the most nice thing, or like where it gets most clear, is this about summarization. Just imagine you want to have a tool which can summarize your long text. So again, you want to do this task of summarizing something into a next word prediction task. Then it's good to look into where are like a lot of summaries happened in just data out there. Because this next word prediction task, what you really might have to do is you have to like transfer your task into something that is commonly done on your training data, so that the model can do what it anyway is good at. And I guess you all know that there's a lot of times these emails or websites where there's a very long website And at the bottom, you find this abbreviation, too long didn't read, and then there's a short summary of what is on the website. So if you're doing next word prediction and you've seen millions of websites, the model hopefully learns that if there's TLDR, following that is a very short summary of what happened before. So we're using this now, so transferring summarization into that, and we're just putting our text, we're putting TLDR, and then ask the model, do the next prediction, and if it is good tuned and fine, it should then generate a summary of what was happened before. So we are changing any type of task into a prompt, and then we can do like a natural language description of the task in the prompt, and you're able to like really do tasks that you might have not seen before and can't be solved otherwise. In generally, these types of prompts, there's different ways. So the most commonly thing is you have something like prefix prompt. So you have all the text before the output. So we have a template like English double point. You have your input German double point. And then typically, if you see this type of thing, then the translation is coming. So you even don't have to say your translation. Again, if you want to do like do that right, what you have to do is like, what is commonly seen by the training? How can I make my task into a best next word prediction task? You can also have something like that. So if you want to do movie reviews or like classification, is it a good, bad, or something? You put your input, and then you have overall it's that movie, and then here it should give you a bit of a rating if it's a good, bad, or something like that. So in all these cases, you're mainly like transforming your task into like this type of prompt so that the task can be solved as a next word prediction task. Any more questions to that? Yes?
But there's also this concept of meta learning, right? That some argues that it comes in automatically with like having a very, very large model. And this is in a way even stronger than prompting because you don't need to engineer into a next word prediction part, but like next word prediction itself is, I feel like, able to solve a lot of tasks in a zero-shot manner automatically. So what are your thoughts on this?
I mean, the meta learning is very interesting. So the idea is there that you learn how to like then easily learn new tasks. But at least there typically you need some examples to do better. So I would more see it as like a different direction depending on your use case. But therefore, yeah, meta learning is definitely also it's more like in your pre-training, your optimization is not to do like next word prediction or so, but you're directly trying to optimize that it's easy to learn the new tasks. And maybe in this direction a bit. So what you can then extend that is if you don't want to do a description of what should be done, you can also give examples. And that also works, and that is called an in-context learning. So you should be a bit careful because there's not what we typically assume in learning happening in neural networks. But what you can do is you can demonstrations of your answers and give them as a prompt. So for example, instead of like having the input add two numbers 6 and 8, you do 1 + 1 is 2, 2 + 5 is 9, 6 + 8, and again, then it's the next word prediction task. So instead of only having a natural language description, these LLMs are also good as few-shot learning, where you just give some examples and then ask it to continue. Again, if it continues, it's like the typical next word prediction task. And that also, I mean, the interesting thing especially is that works with very few examples. So most few-shot learning assume like more than 10 to 100 examples. With in-context learning, you're successful with 2 or 3 examples. And of course, you not only have to do that for numbers, you can also do like translation. You do house and house, car and car, school, and then hopefully the most probable continuation is school. The nice thing is we don't have to change anything into the model, but there's, of course, then other examples, like what examples do you want to select? So how do you show your task? And in which order is also important. So also in this case, there is like some or like a significant amount of things that you have to consider in order to do efficient in context learning. Good. So to summarize, what we did today is we focused mainly on transfer learning and looked how we can do transfer learning, which is somehow the most common thing of how you build machine learning models at the moment. If you have some data, you start with some large models, which you might download, and then you can adapt it to solve your task. What you have to consider is about your architecture and your training. If you want to do several tasks, then you need to think about task representation. And then we found our way from task representations, discrete ones, to more natural one, or natural language ones, which is then going into how you do learning with large language models. So what you should keep in mind is transfer learning, adaptives, fine-tuning, and these are the important concepts that you definitely should remember. Any more questions? Good. Then thanks a lot and see you again next week.
Thank you.